There's a structure inside your body that you have spent your entire life assuming was far simpler than it truly is. Yet this structure has been sending instructions to your brain every single hour of every single day. It determines how hungry you feel, controls how quickly your body processes a meal, expands the more you feed it, and once it grows, it resists shrinking with surprising force. You have experienced its signals without ever recognizing their source. Hunger rising when it logically should have decreased. Stiffness appearing in the morning where there once was none. Insulin becoming less effective despite eating the same meals. Energy fading during ordinary afternoons. And weight loss stopping just as you try to make progress, only to return as soon as you paused. Each of these felt like separate signs of aging or minor bodily failures. But in reality, they were all instructions coming from one place. That organ is your body fat. The fat beneath your skin and the fat tightly wrapped around your organs have been active from the moment it began to accumulate, constantly communicating with your brain, immune system, muscles, and even the inner lining of your blood vessels. It signals your brain to remain hungry, tells immune cells to stay in a state of inflammation, reduces how effectively insulin works, and slows your metabolism. As this tissue increases, every one of these signals becomes stronger. And as they grow stronger, the tissue becomes even harder to reduce. That is a fundamental pattern, clearly stated so you can carry it forward as the explanation deepens. Multiple signals originate from this tissue and form interconnected loops. Each loop alone can encourage more fat accumulation, but together they create a powerful system that resists nearly any single effort you make to change it. This leads to a basic but critical question. What exactly is this tissue producing, and why would stored energy be sending signals at all? The answer is that storing energy is only a small part of its role. In fact, by mass, fat is the largest hormone-producing organ in the human body. Every individual fat cell functions like a tiny gland, continuously creating chemical messengers and releasing them into the bloodstream without stopping. These signals travel throughout the body, reaching the brain, liver, muscles, immune system, and blood vessels. Instead of thinking of fat as simple insulation, it is more accurate to see it as a distributed gland woven throughout your entire body and connected to nearly every system that keeps you alive. These signals are important because you have already felt their effects. One of them is a hunger-regulating hormone produced in proportion to the size of the fat cells. Another helps maintain insulin sensitivity, yet it decreases as the cells grow larger. Two others promote inflammation and rise alongside the expansion of the cells. One directly interferes with insulin function, while another is an enzyme located within the fat tissue itself that produces a stress hormone locally, the same hormone your adrenal glands release under pressure. The key factor that controls everything that follows is how these signals change as the cells expand. As fat cells grow, the balance of signals shifts. Protective signals decline, while harmful ones increase. In essence, the organ rewrites its own messaging system as it grows, and it does so in a way that works against you. This shift continues steadily, tipping further as the tissue increases. The first signal to shift is the one that determines whether you feel full at all, and this is exactly where the problem begins. Your fat cells produce a hunger hormone, known as leptin, and each cell releases it based on its size. The larger the cell, the more leptin it produces. That leptin travels through your bloodstream into a small, deeply located region of the brain called the hypothalamus, which interprets leptin levels much like a driver checks a fuel gauge for the entire body. A high level is supposed to signal that energy stores are full, encouraging you to eat less, while low level signals that energy is running low, prompting you to seek food. For much of your life, this system works quietly and effectively. You gain a small amount of weight, leptin rises, appetite naturally decreases, and your fat cells gradually return to their previous state, without you ever noticing the process. This is where it becomes important to slow down, because the same hormone behaves very differently depending on how long the condition lasts. In short-term weight gain, the system functions exactly as intended. You gain a few pounds over a couple of weeks, leptin increases, the hypothalamus detects the rise, your appetite genuinely drops, and you begin eating slightly less without conscious effort, allowing the cells to shrink back. The system corrects itself. This is the version of the body most people believe they still have. However, when the weight remains elevated, not for days or a single month, But for years, the system shifts into a completely different mode. Now the brain is exposed to continuously high leptin levels day and night, and over time it begins to adapt to this constant signal. The receptors in the hypothalamus that detect leptin gradually reduce their sensitivity. They respond less and less to a signal that never stops arriving. This is the same adaptation your body makes when insulin levels remain chronically high, a gradual reduction in responsiveness, a quiet dampening of a signal that is constantly present. As a result, your fat tissue produces a large amount of leptin, but your brain, now adapted to this persistent flood, interprets those levels as normal. Your energy stores may be full, yet the brain reads them as insufficient, and hunger remains. Over time, your brain has effectively reset the level of stored energy it tries to defend. Consider that carefully. The system designed to alert you has adapted to the alert itself and stopped responding. This is not something you can simply overcome through logic or willpower. The reduced sensitivity of receptors is a physical change in brain tissue, not a mindset you can adjust. And the issue does not stop there. Leptin must also pass from the bloodstream into the brain to be detected. And at higher levels of body fat, this transport process becomes less efficient. This means that even less of the signal reaches the hypothalamus. The message is stronger than ever, yet arrives weaker than ever, failing both at entry and at reception. You may fully understand that your body has sufficient energy stored, but the hypothalamus relies on chemical signals, not conscious awareness. If the signal is high, but the receptors cannot properly detect it, the brain continues to send signals to eat. No amount of determination can override what a desensitized receptor reports. There is a familiar pattern here seen elsewhere in the body. The pressure sensors in your arteries behave in a similar way. When blood pressure remains elevated for long periods, baroreceptors, small sensors embedded in vessel walls, gradually recalibrate. They stop identifying high pressure as a problem and begin treating it as normal. The sensor adjusts to match the very condition it is meant to correct, and once it has adapted, it no longer triggers a response to fix it. In much the same way, your hypothalamus has adjusted to high leptin levels, accepting them as baseline. A sensor has shifted to align with an unhealthy state, and now treats it as standard. A similar, slower adjustment influences how your body responds to food intake, where thresholds gradually shift beneath signals that persist beyond their intended range. This often follows the exact same logic. When a sensitivity setting shifts, the signal continues, but the body gradually stops responding to it. Keep that image of a drifting sensor in mind, however you visualize it, because it quietly underlies far more of the story than it first appears, and it will return again later in a different form. The first time I realized that a sensor could drift and begin defending the wrong level, I stopped seeing hunger as a reflection of discipline and started viewing it as a measurement shaped by its past. That shift, from judgment to calibration, is one idea I return to repeatedly. So hunger is explained. The brain has reset its gauge. But what happens to the food you actually eat? The answer moves in a direction most people would never expect. Your fat tissue also produces a protective hormone called adiponectin, and it is one of the few signals your body gradually loses. When present in healthy amounts, it increases insulin sensitivity in muscles and the liver, allowing sugar to be cleared from the bloodstream efficiently. It also reduces inflammation and helps maintain flexible, healthy blood vessels. Smaller fat cells release it generously, but as these cells expand, adiponectin production declines. Why would a cell reduce the production of something beneficial? The reason comes down to basic physical limits. When a fat cell grows beyond a certain size, it outpaces its own blood supply. The small capillaries feeding it cannot expand quickly enough to support the increased volume. As a result, the inner regions of the cell begin to experience low oxygen levels, and the internal systems of the cell come under stress from maintaining such a large structure. Under these conditions, the cell reduces the activity of the gene responsible for producing adiponectin. It becomes survival adjustment. The cell changes what it produces simply to cope with its own size. This decline, where protective hormone levels drop as fat cells enlarge, was mapped clearly by researcher Dr. Kenji Sato, whose observations turned the theory into measurable evidence. You can begin to see the pattern forming. As body fat increases, two major changes occur at the same time, both pushing in the same direction. The hormone that supports insulin function decreases, while another signal that interferes with insulin begins to rise, a molecule known as resistin. In lean individuals, adiponectin levels are high and resistin is minimal. In individuals with more fat mass, the pattern reverses. Adiponectin drops and resistin increases. One tissue, delivering an entirely different message, simply because the cells have grown larger. This reversal builds on stress that insulin signaling was already facing. The receptors had already begun to lose sensitivity due to constant stimulation. Now, the hormone that helps maintain their function is reduced, while another hormone actively disrupts them. Three separate influences, each arriving through a different pathway, converge on the same result: reduced insulin sensitivity. And importantly, none of these changes would be clearly visible on a routine blood test. The fasting value a doctor reviews once a year reflects an outcome long after these underlying signals have been shifting quietly over time, with protective signals diminished and disruptive signals increased. The result is something many people attribute simply to aging. Consider persistent, low-level discomfort in joints, the minor wound that takes noticeably longer to heal than it once did, or the subtle feeling of internal warmth. These are signs of inflammation, and enlarged fat cells directly contribute to it. They release key signaling molecules, particularly tumor necrosis factor alpha and interleukin-6, and the production of these molecules increases as the cells grow larger. These substances enter the bloodstream and create a continuous, low-grade inflammation throughout the body. This inflammation is often reflected in routine lab tests as an increase in C-reactive protein, a marker that tends to rise closely alongside body fat levels. So the number your physician monitors for cardiovascular risk is, in part, a reflection of how actively your fat tissue is signaling. The connection between enlarged fat cells and the inflammation that disrupts metabolism was clarified by researcher Dr. Daniel Voss, who identified the fat cell itself as a central driver the condition promotes. This low-level inflammation is far from harmless. It damages the smooth inner lining of your blood vessels, interferes with insulin signaling through yet another independent pathway layered on top of the ones already in play, and even affects the lining of your gut by weakening the tight junctions that are meant to keep that barrier sealed. In this way, fat tissue quietly compromises a boundary in your body that you would not normally associate with it. The fat stored deep within the abdomen has a particularly strong effect because of its proximity to major blood flow, meaning it signals inner circulation with minimal dilution compared to the softer fat beneath the skin. The key point to recognize is this: the aches, the slower recovery, and the persistent sense of internal strain you may have attributed to aging all originate from a specific source. That source is enlarged fat tissue itself. Addressing inflammation without reducing the fat that produces, it is like trying to clean a floor while the water continues to run. The inflammation remains because its source remains. At this stage, fat is clearly driving the inflammatory process, but its most strategic response appears when you begin to lose weight. What can shrinking tissue do to defend itself? Anyone who has lost significant weight and then seen it return has already encountered this mechanism, even if they followed the same habits. That regain is not a personal failure. It is a biological response performing its intended function. As you lose weight, fat cells shrink and leptin levels decline. Your hypothalamus, still operating with the adjusted baseline it developed during years of higher weight, interprets this drop as a serious threat. To the brain, falling leptin signals a critical shortage of energy. Historically, this condition has meant one thing: starvation. In response, the brain activates survival mechanisms. It engages three primary pathways at the same time. The first is hunger. The brain increases production of ghrelin, the hormone that drives the urge to eat, making you feel hungrier even while consuming less than before. This persistent hunger is not a failure of discipline. It is the brain defending the level of energy it has learned to maintain. At the same time, the signals shift together. Hunger increases while fullness signals decrease, pushing your appetite strongly in the direction of eating just when you are trying to reduce intake. The second pathway involves metabolic rate, and this is often the hidden factor behind unsuccessful diets. The brain reduces thyroid hormone output, effectively lowering the rate at which your body burns energy. The active form of thyroid hormone declines, and the nervous system activity that supports energy expenditure is also reduced. The outcome is precise. After significant weight loss, your body burns fewer calories than someone of the same weight who is never heavier. Even though the body appears similar, its energy use is lower. This difference can persist for months, and in cases of substantial weight loss, even for years. Long after dieting efforts have stopped, the body continues to behave as though it is in a state of scarcity, conserving energy and waiting for lost reserves to be restored. The third pathway operates without conscious awareness. You begin to move less without deciding to. Small, unconscious movements decrease. You fidget less, shift less, and take fewer incidental steps throughout the day. These subtle reductions in activity can significantly lower daily energy expenditure. Physiologists refer to calories burned through these spontaneous movements as non-exercise activity, and this quiet reduction further supports the body's effort to regain what it has lost. Restless, and that entire quiet system of everyday movement gradually declines while you may not consciously notice any difference. 3 separate mechanisms, all controlled by one brain, interpreting one declining signal. Researchers eventually captured this process in detail. The full range of substances released by fat tissue was first outlined in human studies by Dr. Marcus Hale and Dr. Victor Stone, who identified the many hormones this organ sends into the bloodstream. The body's resistance to weight loss was later measured directly by Dr. Alan Reed and Dr. Stephen Cole, who guided individuals to control weight reduction and then monitored their metabolism breath by breath inside specialized metabolic chambers, revealing just how much energy expenditure had been reduced and how persistently it remained suppressed. This explains why rapid weight loss so often leads to rapid regain. The faster leptin levels drop, the more strongly the brain interprets the situation as starvation. Whether a slower, more gradual reduction allows the brain to adjust more smoothly is still debated. Some evidence suggests a gradual approach may help ease the adjustment, while other studies indicate that the reduction in metabolic rate occurs at a similar level regardless of how quickly the weight is lost. What is certain is that the body's defense of its weight is real. Whether its intensity depends on the speed of loss remains an open question. So metabolism defends a weight. Hunger defends a weight. Even your unconscious movement patterns begin to defend the weight. All of it is coordinated through one signal, leptin, interpreted by one central system, your brain. This allows the full picture to come together. Everything discussed so far points toward a single concept that deserves to be stated clearly. Your body maintains a defended set point for fat, a level it considers normal and actively works to preserve. This level is not fixed at birth. It is shaped over time based on how long you remain at a certain weight. If you live at a higher weight for extended periods, the set point gradually rises to match it. From that point forward, the body treats that higher level as its baseline and works to maintain it. Now imagine the system operating all at once, like 4 interlocking gears on a single axis. The first gear, as fat increases, leptin rises. The brain recalibrates. Hunger remains elevated, and additional fat accumulates. The second gear, as fat expands, adiponectin decreases, insulin sensitivity declines, and more blood sugar is directed into storage as fat. The third gear, inflammatory signals increase alongside fat growth, further disrupting insulin function and pushing even more energy into fat storage. Driving all of these is a fourth mechanism, an enzyme within fat tissue that converts inactive stress hormone into active cortisol directly at the site, regardless of what your adrenal glands are doing. Cortisol has a distinct effect, making this fourth gear particularly influential. It promotes fat storage in the deeper regions around your organs, known as visceral fat, which is the most metabolically active and disruptive type of fat. Subcutaneous fat beneath the skin is relatively stable, but visceral fat behaves very differently. It releases its signals directly into the portal vein, delivering them first to the liver before they circulate elsewhere. This means the liver receives a concentrated exposure to inflammatory signals, fatty acids, and other substances, amplifying their impact. 2 individuals at the same body weight can have very different levels of visceral fat, and the one with more of it experiences a much stronger activation of this entire system. This fourth mechanism not only increases fat, but directs it to the area that intensifies the cycle the most. For interconnected systems, all reinforcing each other, each strong enough to sustain the process on its own. And within this system, the earlier concept returns, the drifting sensor, now embedded within multiple parts of the cycle, quietly maintaining the set point from within. The hormone leptin, central to this entire process, was first identified and studied in depth by researchers Dr. Andrew Keller and Dr. Samuel Grant, whose work transformed the understanding of fat from passive storage into an active organ with a regulatory role. Each of these feedback loops was established independently through extensive research over many years. What brings them together is a single framework that shows how all four operate simultaneously, one organ sustaining itself through every hormonal pathway it controls. That is the central idea this narrative builds from those separate, well-established findings. Each mechanism has been proven individually. What is presented here is a combined system, functioning as a single machine. There is a clear reason why one type of tissue can defend itself so effectively. It communicates with everything. As a gland, it influences the appetite center in the brain, the insulin response in the liver and muscles, the inflammatory state of the bloodstream, and the stress-related chemistry throughout your organs. With influence over all these systems, it has access to every pathway that could potentially reduce it. Describing fat as intelligent would be misleading. Rather, a signaling organ of the size and connectivity naturally affects every possible route of change, and in doing so, can quietly limit those routes. Its wide reach becomes its defense. This explains why a single change rarely produces lasting results. Adjust diet but neglect sleep, and the cortisol-related mechanism continues operating. Increase exercise but overlook stress, and that same pathway remains active. Reduce calories without realizing that your metabolic rate is being lowered at the same time, and you end up working against a system designed to resist with equal force. This also clarifies why intense exercise alone often fails to deliver expected results. Physical activity is beneficial. It activates energy-sensing processes in muscle and helps remove glucose from the bloodstream through pathways that do not rely entirely on insulin. However, at the same time, the hypothalamus may be reducing overall energy expenditure, lowering metabolic output, and subtly decreasing spontaneous movement. The reduction in forces can outweigh the calories burned during exercise. In effect, effort is added in one area, while energy use is quietly reduced in another. Exercise remains valuable, but on its own, it is often insufficient. And now the reason is clear. There is one final detail to consider, and it involves the speed of change. Your body does not respond only to your weight. It also responds to how quickly that weight changes. Like many biological systems, it adapts based on the rate and magnitude of change rather than the absolute level. If weight loss occurs gradually, the brain may slowly adjust its set point downward over time, easing away from the higher level instead of resisting it all at once. This reflects the earlier uncertainty. The strongest defensive response appears when change is rapid. The same principle explains why routines that once worked eventually stop being effective. The body adapts to repeated stimuli, countering consistent inputs until the effect stabilizes. Weight loss is simply another form of stress, and the body responds by adjusting until the effort and resistance reach equilibrium. The plateau many people experience is not failure. It is the system successfully maintaining balance. What emerges from this understanding is a different way of viewing the body. Symptoms are signals from an active system, not evidence of personal weakness. This perspective often lasts longer than any specific diet. Throughout the entire process, fat has been functioning continuously, and energy storage is only a small part of its role. It has been producing leptin, gradually resetting the brain until hunger becomes a steady background state. It has been reducing protective hormones as it grows, removing support for healthy insulin function. It has been generating inflammatory signals that are often mistaken for normal aging. It has been producing stress hormones locally, promoting the accumulation of the most metabolically harmful fat. And when weight loss finally begins, it responds by lowering energy expenditure, increasing hunger, and reducing unconscious movement for an extended period. Fat is not passive. It is an active organ, and that organ produces the very signals that make it harder to reduce. The underlying connection between symptoms often attributed to aging is that they originate from a single source. The fat is the origin. The hormones are the signals.